So I still want to stress that if you want to do my assignment, right, make sure you know the definition really well. Okay. Because sometimes if you start, right, most probably, you start with the wrong thing. Okay, this is what I experienced just now as well. Most probably you start with wrong stuff. Okay, that's why you will get stuck. So you need to go back and check your definition, check your assumption, check your starting point. Okay, this is logical. Why cannot work? Because maybe something is wrong before. Okay, maybe the axiom you use is wrong. Okay, so you need to go back and check. So you cannot just start there and then stop. You need to go back and then forward, go back, forward, go back, forward, go back, forward. This is the process of mathematics. Okay, it's not copy paste. It's not copy paste. Look at example paste. Look at example paste. Not like that. A lot of people can do that. So we should develop a different skill. Okay, let's return to where we left yesterday. So where we left yesterday. Okay, the last thing we did yesterday was So we introduced the concept of open ball. Here we introduced the concept of open ball in a metric space. So we have a metric space, a set with a metric on it, and then what? We introduce open ball. What is an open ball? What do you need to specify an open ball? You need a center, right? You need a center first, and you need the radius. Okay, so what's this ball here? Ball of radius r. Okay, so for example, you can write in a set form. That's why we start with set theory. All the points that are distance strictly less than r from the center. So like what I've shown you yesterday, this ball might not be round. Okay, it could have different shape, depend on your metric. And depending on your metric, you can have different shape. For example, the Euclidean metric on Rn give you the sphere, okay, and sub norm in R2 give you the square. Right? For example, yesterday we've drawn it, and then we introduce neighborhood. Okay, so what's the neighborhood of S? So neighborhood of X. So let's say this Y is a neighborhood neighbor. Okay, it's a neighborhood of X if you can find a ball around X such that this ball lies inside the neighborhood. Okay, lie inside the set. And then we'll call it a neighborhood. And finally, we say that the set S is bounded. Okay, let's say we want to say that this neighborhood is bounded. What do we do? We say that this neighborhood is bounded. So let's say Y is bounded. What can we do? Bounded by what? What can we bound it by? If we can find a open ball, okay, that bounded, okay, maybe bound by a ball. So it's bounded if Y is in the ball of maybe, let's say, rho, okay, around Y. For some Y, so yeah, let me see. Yeah, for some Y in X and for some rho. Okay. Does it make sense? If a set is bounded, you can find some open ball to bound it. This is what we introduced yesterday. Any questions so far about this? This set here. So far okay? So far so good? Okay. All right. So yesterday we left with a very strong statement here. Okay. In fact, if S is a bounded subset of a metric space, okay, say you can bound it by some ball. Actually, you can bound it by balls at any point in X with some radius. Okay. So you see, we go from existential quantifier to universal quantifier here. Okay. So you can really, if your set is bounded, you can start at any point in your metric space and then build a open ball that bound the bounded set. Okay. So yesterday, how do we suggest this? How do we suggest this? So what's the picture here? Say we have a X here, right? I have an X here. This is my space. And then I have some maybe weird subset here, which is bounded. And we know that there exists some ball that could bound this because this is bounded, right? Point X here, and then radius R. And my claim is whenever I start a Y here, I can find a ball, okay, that bound the set, okay, that contain the set. Be a bit careful. We are using open ball here. So what is the suggestion yesterday? We can use the distance between X and Y, okay, to build a ball. And I can include the radius of the ball that is given by the condition of bounded set. And then we're trying to prove that the ball of radius dxy is the ball we want. Okay, so we want to prove this. So let's try it. So let's try. So let's write this picture into words. Assume X is in some ball centered at X. So this is given by the since X is bounded. So we can find such X and such R. Things X. And then we start with any point in my metric space. Then our claim is the ball of radius R X is actually a subset of ball of rho at Y, where this rho is what we have suggested yesterday, R plus dxy. Okay, so once we have shown this, S will be a subset of B rho, correct? B rho 1, because S is already bounded by BRX, contained in BRX. So how do we show this? This is a subset inclusion, right? So we need to show that for every X in BRX, X is in BY, B rho Y. Okay, so we need to show this. Right, so let's say take that in BRX. Okay. So that dzy is less than rho to show that it is in the ball, right? Okay. So consider what is dzy here. Okay, how you relate dzy, okay, to the distance of z between x and x between y. You can use triangle inequality, okay, very useful. In metric space, almost one thing you always use is triangle inequality. dzy is less than or equals to dzx plus dxy. But what is dzx here? Z is in x. Sorry, Z is in the ball of radius r around x. So meaning it is strictly less than r. Okay. How about dxy? Dxy is just dxy. Is their distance. So what is this? This is by construction. Oh, okay, this is by construction. So we have shown that the distance between dzy is strictly less than rho, which means this z is actually lies inside the ball of radius rho with 1. Okay. And so z is in by. Okay, so easily follows that since s is contained in brx, contained in b rho y, it follows that s is in b rho. Okay. Yeah, no? Does it make sense? Okay, we just use triangle inequality here. Okay. Any question? So far, so good. Okay. Okay, let's continue. So you can see that the boundedness is not like you can really bound it anywhere you like. Not that anywhere you like, but you can bound it with ball and with any radius. Sorry, with any center. Okay, but not with every radius. Not with any radius. Okay. All right. So next, we will continue to talk about, for example, what's the notion? Okay. Notion of a point being strictly inside, okay, or strictly outside, okay, on the boundary of set. So what are the notion of being strictly inside a set, outside a set, or at the boundary of set? Okay, so we have to be very clear about this. Okay, what's your job? What's not your job? What's the thing that you can juggling between? Does it make sense or not? Does it make sense? So what I want to say is, by learning this, right, you need to learn how to determine what's your job and what's not your job. Okay? What's inside a set, what's outside a set, what's at the boundary of the set. Okay, so that's a definition. So suppose there's a subset inside your metric space. Okay. So what's a point inside your subset? A point is an interior. Okay. Interior point of A if, okay, if some open ball centered at X is a subset of A. Okay. So, right. So how can you say that you are inside this classroom? Okay. You must be a bit away from the door. Correct? you must have some distance away from the, later we'll define what is boundary. So you must have a room between you is also inside the set, so that you can say that you are inside X, inside A, sorry, inside A. Okay. How about outside? Okay. So how about exterior? So let's copy this. How about exterior point? How about exterior point? You want to guess? What's exterior point? How do you make sure you are outside the classroom? Same definition, except you change A to the AC. So you have some room before you coming into this classroom. Okay. So you have an open board around you. It's also outside. Okay, outside the set. How about boundary here? How about boundary? How about boundary? So if every open board centered at X contains at least 1 point, okay, of A and at least 1 point of C, 1 point of AC, complement of C, then S is a boundary point of standard boundary point. Yeah. Have you ever go overseas? Have you go overseas or not? Or maybe have you go overstate? Okay. So what's the boundary? Let's say where's the boundary between Malaysia and Singapore? Huh? Where? The sea. Okay, let's say you can stand on the sea. Okay. So I mean, okay, let's draw here. Let's draw here. So maybe like this. Okay. Let's say they are connected like that. So maybe here is Malaysia. Right. Here is Singapore. So I claim that this green line here is the boundary. Well, why is it a boundary? If you stand on the boundary, right, you step a little bit to the top is Malaysia. You step a little bit to the bottom is Singapore. So meaning that if you have an open ball around you, okay, any open ball, okay, it will contain 1 point from Malaysia, because if you set up Malaysia already, step to the top Malaysia, step to the bottom Singapore. No matter how small the ball you make, then you are at the boundary. Okay, so this is the boundary. That makes sense? Okay. So for every ball you make, no matter how small, right, it will contain at least 1 from the inside, 1 point from inside, 1 point from outside. Okay, outside the set. Okay, A and A complete. Okay, so this is a boundary point. Okay. So next notation wise, we just say that the set of interior points of A is called the interior of it. So we don't say interior points of A. So if we collect all interior points, we just say interior of A. Similarly, if we collect all the exterior points, okay, we will say that the set is the exterior of A. So first, we will denote by int A, okay, and the second one we will denote by XA, okay, exterior of A. And the set of boundary points we will call the boundary of A. They form the boundary. So the points form the boundary. The boundary points of A is called the boundary of A. Called the boundary. So how do we do this? How do we denote this? We will write it as partial A. Partial A. We'll write it as partial. Boundary of A. Okay, right. Thanks. So next we will study what's the relation between these points. So what do you expect from these points? So let's suppose a subset in our metric space again. Okay. So what do you expect? What do you expect about these three set of points? Three disjoint. Sure. Okay. So actually you can prove that your metric space can be decomposed into int A union with boundary of A and union with exterior of A, such that they are mutually disjoint. Okay, so their intersection is 0. So their pairwise intersection is 0, mutually disjoint. Okay, let me write all of them. Okay. 2. What else? The exterior of A, okay, should be equals to the interior of outside A. You know. Okay. And the interior of A is the exterior of AC. If you can get the first statement, second statement is immediate. What else? Interior of A is always a point in A. Okay. You might want to think why the other direction is false. And exterior of A is similarly a subset of AC. All right, so let's discuss about this statement here. So for the first part, right, is it clear that Y in A, partial A, and exterior of A are mutually disjoint? Sure, by definition. Of course, by definition. But I mean, how to say? So let's say S is in the interior A, right? What does it mean? You have a open ball around you, which is completely in. Okay. Can this kind of point exist in the boundary or not? In boundary, what you will need to satisfy? Any ball you make around it must contain at least one outside, one point outside, and one point inside. But in A, there's one ball that cannot be there already. So it doesn't work. Okay. How about exterior of A? The outside, point outside AC, and then you have an open ball around it. But if you are pointing in A already, you are pointing. So that ball will contain some point inside A, not in AC. So similarly, you can argue for the other intersection. And is this union clear or not? Is it clear? So I think right to left should be easy. Right to left is easy. Left to right. If you are ball in a metric space, what can you do? How can you show that for every point in X, it is one of them? Oh, right? Union, union means all. So you need to simplify one of them. Okay, so if you have a point in metric space, how do you show that it is either in A, either in delta A or either in XA. How do you show that? Any idea? How do you decide in A, gamma N, and XA? What's the tool you use to decide these things? Open ball, right? So you have to look at the open ball around the point, okay? So first of all, surely you will know that X is just A union AC, right? Surely this is surely not. Okay, so see how this A and AC decompose into these three things. Okay, if you are point in A, okay, what can you do? Form an open ball, right? Form an open ball. And then this open ball, what can you see? If this open ball contains all the points inside A, right? Then you are the point in A. But let's say this open ball contains something outside, something inside. What happened? Sorry? Not yet. In delta A, you need to show for all. I just say there's one, but there's something outside, something inside. Doesn't imply that you are at the boundary. You know what happened? You know what happened here? So let's say you are in JB, okay? You make your ball so large that you include some point in Singapore. Does it imply that you are at the boundary or not? No. Try and make the ball smaller. Okay? Try and make the ball smaller. Try and make the ball smaller. If you can make it smaller until it contains everything inside A, then you are interior point. But let's say you cannot do it. You cannot do it means what? You are on the boundary. Okay. Okay, you need to check for all. So very important, existential quantifier and universal quantifier, very important. Okay, very important. Okay, so we settled this. So really, really what? Really, these are the two possibilities for points in A. How about AC? So if you have a point in AC, you do the similar analysis. Okay, you put a ball around it. You put a ball around it. Yeah. And then you check that it can be either in XA or either in delta A. Can it be in delta A or not? Let me see. What's the definition of delta A? It doesn't say that X has to be in A. Okay, never mind. Okay, so AC, you do the same analysis. Okay. Does it make sense? So you just put ball around it and then see. To show that something is a boundary point, you need to check for all balls. Okay, all open balls, not just one. But to check for in A, XA, just find one is enough. Okay, okay, good. How about second part? Let's show for the first equality here. Let's say I have a point in XA. What does it mean? I have a ball around myself, and then I am outside AC. But you are the ball that completely lie in AC. So you are in, let me think. So let me write down here. So let's write down a bit carefully here. So let's prove 2. That if, so let's go one direction. If X is in XA, then S is in AC. Okay. X in A, so since X is in XA, what does it mean? So you have a ball, okay, say radius R, centered at Y, okay, such that X is in this ball, and then this ball is contained in this. Thank you. So it's a superscript. Okay. See, this ball is contained in AC already, right? Right. So this means that X is in the interior of AC. Then you can show the other direction. Okay. So the other direction should be. So once you have XA equals to in AC, you can straight away deduce in A equals to XAC. You know how? You know how? When trying you want to say. Oh, once you have XA equals to in AC, complement of A, you can deduce that in A equals to exterior of AC. You know how? First, of course, you can go through the same proof, similar proof, but my claim is you can straight away deduce. Right? Yeah. So you just set A equals to AC. Right. So you can set A equal to AC. So this will imply that X of, because A is a random subset, right? So you can set A equals to AC in XAC equals to in ACC, but ACC is A. Okay. So set theory comes in again. Okay. Okay. 3 is quite trivial. I think you can show it yourself. But the non-trivial about 3, right, is why the other subset inclusion is not true. Okay? Try and think about counterexample. Why there's no equal sign there. Okay? That subset inclusion is by definition already. Yeah. Okay, but how about the other direction? Why is it not true always? Okay, you need to think about counterexample. Maybe later in the course we will see some counterexample. Okay. All right. Next. So let's go a bit further before we take a break. Definition. So suppose A is a subset again, okay? And we want to look at a special point. Okay, what does this point do? First, I called it a limit point. Or maybe in some literature, you will see it as a cluster point. Or sometimes they call it accumulation point. So you can see that these words, right, somehow hinting what this point is doing. There's a cluster formed around it. There are points accumulate around it. And it is a limit of some point. But sometimes you need to be a bit careful. I made a remark here. Sometimes this cluster point, accumulation point, limit point in certain literature, maybe very old literature, they have slightly different meanings. Okay, so you need to be a little bit careful. But here, we just regard them as the same for now. Okay, just regard them for the same for now. But I think I will always use a limit point. Okay, of A. Okay, if every open ball, using open ball again. Okay, so in this chapter, always we will use open ball as our tool to measure things. Okay, if every open ball centered at X, okay, contains at least one member of A other than X. Okay, does this make sense or not? If you are a limit point, every open ball around you must contain at least a member of A, which is not you. For example, you see, you guys sit like this, you guys not a limit point. You know why? Yes, correct. In fact, you are just discrete or isolated. So if you want to be a limit point, everybody must rush for you. Yeah. Does that make sense? So you need to be an accumulation point. A lot of things should accumulate around you that cannot separate from you. Does that make sense? Does that make sense? Okay. So just now I touched the concept, right? So a point x in A is an isolated point if the sum open ball, okay, centered at X contains no member of A other than X itself. Yes.
Limit point, why don't you use the limit point we used to have, but you use this definition?
Which definition?
I think I remember.
For every epsilon.
No lah.
Sequence of point, yeah. Yeah. You say what's that? For every epsilon, right?
You are a point and then you have a sequence of point. If you want epsilon, is okay lah. It's another equivalent definition.
I mean,
or is it any other case? Is it any other case that the point you're containing is not converging towards the X?
They are equivalent actually. Actually, they are equivalent, right? If you want to talk about sequence, so from here you can build a sequence. You have one ball, there's one member, right? Other than X. Pick that one as a term in your sequence. So make a smaller ball. Pick another one. Make a smaller ball. Pick another one. So form this sequence and then show that this sequence actually converge in your sense.
But if we take the sequence is constant.
So that's why here says that contains at least one member other than X, right? So you can build non-trivial sequence. Yes, non-trivial sequence. Like what you said, I can build a constant sequence, that one as a limit access, but I don't want this trivial thing.
Like this, that may minus X.
Yes. Yeah. So you see here say that contain at least one member other than X. So you can pick another thing other than X as your. Wait, not A minus X, it's the ball minus X. A minus X a bit big. We want to form a convergence. Yeah, sure. Yeah.
What we can say is not an isolated point, right? We just because I think if you define this way,
it's the same. It's the same. How about we make this an exercise?
But we can take step. We can take step. Limit point cannot take.
No. How to say? Wait. So no. I mean, wait. What's the question here? So your question is, does this convergence similar to sequential convergence, right? So question, right?
yeah,
so much. You can build out a sequence that converge to this limit point using this for business. Yeah. I think you are talking about slightly different thing. Ball to sequence. From sequence to ball. So what does sequence do? Is that my limit point or not?
Because it
Mm.
we take the
Yes, that's right. That's right. Yes, slightly different. Yes, you're right. Yeah, slightly different. Yeah. Mm. Any question about these two concepts or not? So you see, one concept we use every ball, one concept we use that exists ball. Okay, so in mathematics, usually we just play around with these two quantifiers. Okay, so we talk about limit point and then isolated point. Okay, next definition. So we define the closure of A is the union of A and the set of limit points. And we denote it by A bar. Okay, it's like we close it. Okay, closure of A is A with a set of limit points. So one example we frequently talk about is if you have a Q, we take a Q bar and we'll get R. Okay, here bar is different from the algebraic closure. Here bar is the Cauchy completion. Algebraic closure, Q bar is a different thing. Okay, I'm not sure A2 got mentioned about this one, but you get what I mean? Okay, who take A2 here? Who take A2 here? Or take them before also can. Who take A2 here? Just this group. 1, 2, 3, 4, okay. Okay. So another operation is you can take algebraic closure. Okay. That's Q, also called Q bar, but the Q bar here is taking Cauchy completeness. Is you fill in all the limit point of your Cauchy sequence. And then you'll get. Okay, let's take a break. Okay, let's take a break. Let's take a break. Got question or not? No question. Let's take a break. Then we will resume. Let's come back faster, maybe 1205. Okay. And it's how many Yang Ke, you guys come up and discuss a bit.
他回来，对，哦，签证刚好，
好，签证条款啊。你们比较慢回，所以我们已经过了1，然后要丢了3，所以你们大概有看过了吧？有开始做哈。你们觉得你们什么时候可以做？
下个星期上午可以讲。
可以哈 ，OK 可以。你呢？
我这个星期先交，
这个星期先交1、2 ，OK，然后
3本来就是下个星期，
3是下个星期，对，
就之前2的 deadline 是
2的 deadline 是下周一，对，
那就是周日可以交了。
你也跟他一样的，3份可以在下个拜五，可以吗？
可以。
如果不能，你再告诉我。这样目前就这样定了，3份在拜五交了。 如果你拜五前交，如果该来得及啦，至少我可能还可以给你 feedback，但是感觉有点赶。尽量啦，看看啦。但是不能的话就下个周五。如果不能，你再告诉我。下个周，下周3份哈。OK，谢谢。等一下，upload 一个东西先。哎，对，哦，第2题哈。Substitute these extractions for iterations that尽量保持。这是什么东西？
上面我觉得没有错，是
但是我要知道上面有才这样子。对，
就 decimal representation 吧。
怎么有？
然后0.14、0.14就是去有些个小数。
哦，诶，就是说从哪里去？假如1.14的话，那么你的 sequence 是 conversion？哦，因为
我每
improve 啊，
我每一次加一个 positive 的东西下去嘛，
有
那 negative 啊，至少
会去什么东西哦？
我们去这个
你用 irrational 做出来的东西不应该 convert 去 irrational。
对啊，就是这个 F。对啊，去这里的学的
哦，
没有关系啊，我是问这一句。对吗？
这句话有什么问题？这句话没有问题，我是怀疑这句话写出来有错吧？有问题吧？这句话没有错啊，
这没有问题啊。
没有问题。你看你讲没有意思，然后我读看。这样，因为不然的话，我要看看你的东西到底恐不恐。
对啊，
要做好是
那没吧？
没有，不用想。
不一定哎，
没有，
就是他的方法。
我也是用中文，然后那个不是我做，我知道不好现在。你是用中文，
不然你要证明有那个你是用。
Yes。
用不是 flow function 只是一个方法来讲嘛，你可以说是 like 它的就是讲啊，就1.1是什么什么什么嘛，就一个是1.1，一个是1点什么这样。
对啊，
也
就是我们去拍的也可以3给1
啊，对啊，对啊，对啊，然后你要 argue 的应该就是说，来为什么这个东西会convert去原本
那个花花是因为还有那个
大小变化跟和原本数下来的越是
你上面提出那个就已经
老个税里面看错的可能是半个。
他这个跑去 category，
我去哪里？先讲跑去 category。
叫他可以。
哦，
他就问他，他有人问他 free group，你的 free billion group 是什么意思？
啊
然后他就用 category 的
那个
解释那个 free。
universal property 啊，
他不是用，不是我们学的 group presentation，就是他是用那个unique homomorphism，
应该是可以写出那个，
就有点像那个 isomorphism 的。
应该是叫 universal property 耶。
就是他没有讲到，他变成这个什第二就有点，他现在叫 subnormal series，
什么
subnormal series，
什么是 subnormal？哦，subnormal
series，
来做什么啊？到底他教了这个东西来做什么？
我不懂他什么道理，因为他教到后面了，因为他
哦，只是在教 two 罢了啊。
补充。
我学搞 theory 根本都没有用到这种东西。
有学过啊？
我学过搞 theory，
就从 subnormal 就去 composition series。
那个好像离 group 的东西哦，
啊，对，他要讲 liquid，
离 algebra 的东西。
他应该刚上课是用先讲 simple group，
他是拿来算离 algebra 是吗？
然后 simple group 他就去离 type simple group。
对啊，他是拿来算离 algebra 是吗？
他要去 type B 耶，他想还要他 B 跟 C 的。
他不是在教 Galois theory， 他是在教离 group。
我不懂他都有种，还有他的模拟版。
Galois theory 的话，要做 constructible number，然后加那些 root 进去，然后发离，
讲太忙，现在做那么多球友，
是不是？我感觉是，我感觉不是在做个 Galois theory， 是在做用 Galois theory 的东西。OK， hello, testing. Okay, let's return. Any confusion about this concept? Any confusion so far? So far okay. Okay. So let's continue. Let's check some property of this limit point closure, right? So let's check some proposition here. Okay, so one important thing. So a limit point of A need not be a member of A, right? You can converge to something, but that thing might not be inside your set. Make sense? You just give one example. What's the example? Huh? What example you can give? More wafer.
The center is not included in the ball. Like a hole inside.
Yeah, sure. Okay, you can think like that. Okay, you can think like that.
So like interval, you also can get to that point. But
I think like that.
deleted.
Deleted, yeah. Yeah, you can think like that. Yeah, that's the topology way of thinking things. Yeah, you can do like that, like you have a disk and then you take away some point inside the disk. Yeah, you can think like that. How about number? Actually, just now I give an example. Q bar is R. So limit point of Q could be irrational not Q. Correct? Yeah. You could have limit point Q as well, but yeah. And two, if S is a limit point of A, okay, then every open ball centered at X contains an infinite number of points from A. Is this obvious or not? If S is the limit point of A, then every open ball centered at X contains an infinite number of points from A. So just now I just said that if you have a limit point, for every open ball you can find X and other point in A. But now it turns out that this ball will contain infinite many points. Okay. Way to find this infinite points of A. Where to find? Yes, so you can keep building your ball, right? The innumerable many ball, for example. Then this is the infinite at all, right? Infinite is just not finite, right? Yeah, so the innumerable is a infinite point. Okay, good. We prove it. Okay. Next, A is a subset of A bar. Okay, makes sense, right? Okay, makes sense. For every point in A bar, okay, is either a limit point of A, okay, or an isolated point of A. But you cannot be both. Okay. You cannot be both. So what is A bar again? A bar is what? Union of A and the set of limit points. Okay. A and its limit point. Okay, A bar. So a prototype of this, you should think of the real number. So either points in A, either points in limit point. So if you are a point in limit point, then you are satisfying the first statement, first property here, a limit point of A. But the claim here says if you are not a limit point, then you are an isolated point. Okay, what does isolated points means? What does isolated points mean? There exists a ball centered at X such that there's nothing else. This is really the negation of the statement for limit point. Where's the negation? So if P true, not P must be false. If not P true, P must be false. So you can only take one of them. Make sense? Yeah. Great. So this one, okay, about 5. X is in A bar, okay, if and only if every ball around X, okay, with radius greater than 0, contains a point in A. Okay. So how to prove this? So there's a reason we put 1, 2, 3, 4, 5, right? So we can use 4 to talk about point in A bar. So if you have a point in A bar, you are either a limit point or an isolation point. If you are a limit point, let's say we go from left to right. If you are a limit point, then the statement on the right surely satisfied. How about if you are the isolated point? Does this statement satisfy or not? Why? X itself is a point in A. Okay, yeah, X itself is a point in A. Right. How about the other direction? Okay, the other direction. If you have okay, if you are a ball, okay, so every ball around you, okay, contains a point of A. Okay. Does it imply that you are a limit point or you are an isolated point? If you have a ball around yourself, right, contains a point in A, what does it mean? This point of A could be X or could be not X. If it is not X, what happens? Should I draw it? Let's draw it so that you have something to imagine. I also have something to imagine. So let's say I have a ball. Okay. So I'm going this direction now, and the other direction is contribute. So let's say about this. Okay, I have a ball. Contains a point in A. Okay. So this point here could be a point that is not equal to X. Right? Or X itself is in A. So two possibilities. So how to argue? Give here. I should say here not equal, right? One case. You have another point that's not equal. If for all the ball, right, contains a point that's not equal to X, what does it mean? X is the limit point. This is exactly the definition. But let's say for all these balls, there exists one ball such that you cannot find other point other than X, which is in A. Then X is the isolated point. Okay. So either one of these two things must happen. Okay. Try and write it out. Write it out. Try and write it out because yeah, these are just some routine exercise to check whether you know the definition. Any question or not regarding this 5 statement here? Okay, so far so good. All right. So example. So let's look at some example. So let's say we look at this sequence here. I think this is also the sequence we learned in MA1. I gave them prove that this sequence converges to 0 using epsilon n definition. Okay, so this sequence here. What are the limit points? What are the isolated points? What are the isolated points here? Everyone is an isolated point, okay, because you can pick epsilon small such that the open interval, so the open ball here become open interval, right? That don't contain other point. Okay, so everyone is a isolated point. And what are the limit points here? 0. Okay, so 0. Why? How to prove it? How to prove it? Sorry? Hey, what's the definition of limit point? Oh, no matter how small the ball, right, must contain something inside the set. So you fix an epsilon. Fix an epsilon interval there. Okay. Can you find an element of the member? The element of A, okay, which is not zero inside the interval. Can you find that? Or let me do a simple exercise here. Let's recall your MA knowledge. I have a zero here. Okay, I need to show for all epsilon. So let's say epsilon minus epsilon, let epsilon to be greater than zero. Can you find a member? Okay, 1 over n inside this interval here, open for here. Can you find or not? Can. How to find out? Yes, good. Archimedean property. Okay, we can find, so by Archimedean property, there exists a capital N such that 1 over n is less than epsilon. Okay, good. I was like spending the past 2 hours teaching them this using Archimedean property. Different example, we need to use this. So the existence of this capital N, you really need Archimedean property. Okay, how do you prove Archimedean property? You need to prove from completeness axiom. Otherwise, you don't have. So that's why real number is really special. Okay. Next example. Let's look at this interval here. 0, 1. Okay. Open on one side, close on one. Open at 0, close at 1. So what are the isolated points here? No one. How do you show it? How to show this point, this set doesn't have isolated? Negation of isolated point? What's the negation of an isolated point? Sorry? Yeah, sure. Every point is a negative point. Okay, sure. Okay, so the result here is every point is a limit point. Okay, but is it true that all the limit points are just close open interval from 0 to 1? That one? No. But what's the limit point here? Close interval from 0 to 1, you need to include the 0 in. Why? Why? Why 0 is a limit point here? What's the definition of limit point? Recall, what's the definition of limit point? For every ball, you need to find 0 and other than 0, which is in the set A. Can you do that or not? How? It's still using the above result, Archimedean property. So we can show that there are no isolated points. In fact, the open interval, open at 1 and close at 1, open at 0, close at 1 interval are limit points A, and the set of limit point is actually the closed interval 0 to 1. Okay, so meaning here, this half open interval bar is actually the closed interval 0 to 1. So that's how we call it closed interval, open interval. It contains all the limit point. Okay. All right. More time. Continue. Let's continue. So keep going. Theorem. If I have a set in Rn, then what? Then what is A bar here? Okay. A bar is really the complement of the exterior of it. Okay. And what is A bar again? A bar is really the interior of A union the partial of A. Where's partial of A? Limit point of A. Boundary point of A. Okay, it's a boundary point of A. And what is A bar? A bar is A union the boundary of A. What is A bar again? A bar, so let's keep the definition here so that we can discuss at the same page. So what is recall definition of A bar? What is A bar? It's A union set of limit points of A. Is this the definition? I don't know. Let's check. Memory. Okay, good. Okay, so we want to prove this three statements here. Are they obvious? Are any of them obvious to you or not? Maybe there's a reason why they arrange it this way. So maybe let's look at the first one first. So if you are in A bar, okay, you are either a point in A or you are limit points in A of A, not in A of A. Because just now we learned that this point might not be in A. So we want to show that this is in the complement of the exterior of A. What does this mean? What does it mean to be X in the complement of the exterior of A? Say it. So who wants to say this? Okay, keep on. Oh, so you say that this is equals to the in of A union boundary of A, right? Because this is from previous, so this is by X. Okay, so I don't want to fix to X Rn, sorry, let's fix this to a general metric space. So by just now, right, just now we have this result, X equals to XA union in A union. Good, this is true. But so the problem here is, do you want to prove the second one first or the first one first? Let's decide, huh? Okay. So can we straight away prove from the exterior of A without knowing this one? Right. Yeah, right. Okay. Can we do it without knowing XAC equals to in A union delta A? Okay. So I mean, you just use set theory, right? So what does set theory tells you? X in XAC is what? X is in the metric space, but X is not in the XA. Okay. So what does it mean by X is not in XA? Yes, so let's write it down. So to be not in XA means what? There is no open ball around X such that this ball is in AC. If there is no open ball that can dig that, then what happened to your ball? Huh? What happened to the ball? What this ball? This ball should contain something, right? What's the thing can exist inside this ball here? If this ball cannot be in AC. What's the possibility for this ball? This ball cannot fully. So what happened? What can happen to this ball? It could be a ball inside A completely, or it could contain some point inside A or something inside C. Right? These are the two possibilities. But these two possibilities is exactly what? I'm sorry. Sorry. Closure. Yeah. So we want to argue that this point actually is the closure. So what happened here? So X is in X. So this ball, so for ball around X, it could be inside A completely, or this ball X intercept A, and so let me put 1 and 2 here. So it could be the ball intercept AC are both non-empty. Right, not empty. Alright. Okay. So if it is the ball completely lie inside A, meaning what? This point is in A. Okay, good. So it's in A. And second case, if this ball, intercept A is not empty. Intercept AC is not empty. Okay. You need to know that this has to be true for all ball. So this X will be the sure boundary. In other words, actually it is the actually what? This is a limit point. Right? Because you got one side keep having A. Does it make sense? You should think like this, huh? A like AC is like this AAC here, right? You always got some point from A on one side, some point on AC on one side. But if you keep containing point from AC, means you are a limit point. It may be isolated point. No, right? Because this is have to true for all R, right? Let me see. True for all R, right? Don't exist, so for all R must wait. Oh, you mean let me think. So what are you trying to say here? Oh, okay. Oh, you mean there's a third cases, right? There's a third cases. Let me think. Let me think. So I mean, first case include the isolated point, right? Yeah, I think first case include the isolated point. The truth. Isolated point just says that there exists one ball such that it doesn't include any other point. I think first case included. Yeah, second case it just says that it doesn't completely lie inside A. Okay. If it doesn't completely lie inside A and cannot completely lie inside AC, so meaning it have to have non-intersection between the two. Okay. And this is the boundary point as what you said, but on the other hand, it is also a limit point of it. Does it make sense or not? So boundary point actually is a limit point of it. Does it make sense? So every boundary point, every boundary point is a limit point. Because boundary point is stronger, right? You contain something inside and something outside. But to be a limit point, what do you need? You just contain a member that is inside A. Make sense? So what does this mean? This means another thing. This boundary point actually is also a limit point for AC. Yes. Yeah, right. Yes. So boundary is very political boundary is very important. That's why you can see the country will keep fighting over the boundary. Boundary is very important. North Korea and South Korea, they built a tunnel, not tunnel, build some houses, scrutiny houses around that boundary, and then they keep the boundary to like one staircase or something like that. Once you cross it, then you go from South Korea to North Korea. And so very precise. Need to be precise with this boundary. Okay. Does it make sense? Okay. Yeah. Say again.
The set is
Singleton. Okay.
So this element is the
Boundary.
of this set.
Let's check.
And this point is not the limit point.
Let's check. So let's check. So what does it mean by boundary? So you need to say where the set lies. Okay. So where the set lies. So where do you want it to lie? So you lie in R. Okay, let's talk about this. So you want to ask about what's the boundary of the set? Okay, what's the boundary of the set? Yeah. So what is boundary? What does boundary means? What does boundary means? For every open ball centered at X, contain at least one point in A and at least one point in AC. So what's the boundary of this? So every ball you need to contain a point inside A and a point outside C. Okay. Yeah. Okay. So what do you get? What's the boundary of this? You look at every ball, okay, centered at X. Okay, look at every open interval in this case. Okay. If it contains at least one point in A and then one point in AC. So it contains one in A, in particular itself. Right? And then contain point in AC, other thing than 0. Right? Just the open interval slash out 1. Okay, then you will get 1. You get 1. And then what? Is 1 the limit point or not? 1 is the limit point or not? Because like the example given by Yihan just now, right? We don't consider constant function sequence here. Right? We need to contain other point. Okay, so the limit point. How to write? One of the set is empty. Right. Okay, just now what did we say just now? So just now we say that a boundary point. What do we say just now? So a boundary point, could a boundary point be a limit point or not? Right. Okay, so what's the difference between the definition of boundary point and limit point? Because limit point you need to contain other point than X. Okay, but boundary point might not consider other point in it. Yeah, you just require that. Yeah. So then this case, what happened to this case here? So what happened to case 2 here? Oh, isolated points stay inside this category. Yeah. Yeah, I think you're quite true. Wait, let me think. Yeah. Correct. What? Contradiction? Let's say, yeah. So I think the problem here is whether this intersection here contains other point than x or not. If it doesn't contain other point than x, if it doesn't contain other point than x, then it is a isolated point. If it contains other point than x, then it is a limit point. Yeah. Makes sense. Okay. So either, so let me move this down. So either for all BRX intersection A contains other point in A than X, or there exists a ball of around X intercept A is just X itself. Any question about this one? So we have one direction, right? So if it is in there, then we show that it's in A bar. I think this is a if and only if state. So if you are one of these cases, and then I think you can go back. I think these are if and only if statement. Okay. Any question about this proof? Any question about this proof? Yeah. Question about this proof? No. What's next? Okay, so by the theorem just now, okay, x complement of x is just interior of A plus boundary of A, okay. And how about the last one here? Okay, is A bar is equals to A union boundary of A. One direction we know, right? So in A is in A. Okay, so this direction we know. Okay. How about the other direction? If A is in A, surely A is in A. Okay. If A is in the boundary of A, okay, what can happen to this point? I think from the argument just now, right, these points are exactly either isolated point or the limit point. Is it true? It's exactly what we argued just now, right? If you are at the boundary point, what happened to you? Every ball contains a point in A or a point in AC. Okay. If the point in A is just yourself, no other point, then it is an isolated point. If the ball contains other point in A, but not X itself, then it is an isolated point. Sorry, limit point. It's exactly what we argued just now. So the the difference here is the ball you look for when you are considering a boundary point and a limit point. What's the difference? In the limit point, you must contain other thing that is not x. But in the boundary, you can consider all points in A. The ball in boundary, as long as you contain one point in A and one point in AC, okay, it doesn't exclude the center. But for limit point, you need to exclude the center to consider other member of A. So this is a difference here. Okay. Does that make sense? Or question? Okay, in this case, maybe what time is it? 4:06. Let me see. We shouldn't start new stuff. So let's give last proposition on this subject. So let's look at ball. Any ball in the metric space. Then you can prove that the interior of this ball is just itself. Okay, that's why we call it open ball. 2, the exterior of A, okay, is or contain the point that d x y strictly greater than. And 3, the boundary of A is contained in the set of points such that dyx or dxy is equals to r. Okay, and then if I take closure of the ball, okay, closure of the ball, what is it? Is exactly all the point that is having distance less than equal to r with the radius. So you can see that some of them you just have a subset inclusion. Okay. The proof is quite straightforward, but like what I say, what's the counterexample to this non-equality here? Why is it not true that exterior of A is all the point that is distant greater than r from x? Why not all the things that equals to r, okay, all the points that are distant equals to r is in the boundary of A? Okay, why? I think it's just now Soning counterexample is a bit related to this, right? So let's look at one counterexample. Yep. So how about looking at this counterexample? Okay. So set of two things, and I set my distance to be, say, d01 is 1. So this implies d10 is 1. And d00, d11 is 0. Okay, so what we consider here? So let's consider, say, let A equals to ball of radius 1 around 0. Okay, so what's this ball here contain? This ball contains just 0. Okay, and then you can check that the interior of A is A. And what's the exterior of A? 1. Okay. And what's the boundary of A? The boundary of it. What's the boundary of it? Boundary of that means what? Huh? Should be nothing. Should be nothing, right? Open ball, strictly less than 1. Okay. And A bar is equal to A. Okay, so can you verify that this is a counterexample to the 2 subset inclusion here? Right. So I mean this set here is what? It's 1, right? But 1 is not in the empty set. Okay. And then what else? Exterior is this guy. Okay. How about this one? Greater than what? Nothing. Right. There's nothing greater than 1 from each other. So here become an empty set. Here become a set containing 1. And so the other conclusion, the other subset inclusion doesn't work. Okay. Yeah. So I mean, this kind of proposition, right? The equality should be straightforward, but why there's only 1 subset inclusion is very important. You construct 1 counterexample. Okay. Usually, this kind of counterexample is quite easy to construct. You don't need to go for a very hard one, sophisticated one. Okay. Usually, it's quite easy to see. Okay. Okay, now. Any questions before we finish? Okay, so in next class, right, we will try and generalize this open ball to open set concept. Okay, and then from there we will enter topology. Talking about open set and closed set. All right, see you next Monday. No replacement, right? Next Monday, got replacement or not? No. Okay, next Monday no replacement. If you can, please come to the seminar. Check out the news. Mathematics departments, and have you guys added into the Teams group yet? Not? Please find Brian. So we have some informal discussion there. Okay, you can ask questions there.